For the given network over here, we have to determine IL, VL, VR1 and VR2 for 5 tau constants of the storage phase for the first question. Then we have to find the mathematical expression for the same variables during the release phase when the switch is open, and then we have to draw or sketch the waveforms for each voltage and current for both the phases. We have already determined the expression of IL, VL, VR1 and VR2 in the previous example for the storage phase. Hence, over here we have just written down the expressions. However, for the release phase, all the steps for determining IL, VL, VR1 and VR2 are shown over here. At first, we will determine tau, the time constant, which is tau prime for the release phase, equals L by R1 plus R2 and is equal to 0.8 millisecond. We know that Vi is equals to 1 plus R2 by R1 times E, hence Vi equals 125 volts, and VL will be equal to minus Vi e to the power minus t by tau prime, which is equals to minus 125 volts e to the power minus t by 0.8 milliseconds. Now, Im will be equal to E by R1, which is 25 milliampere, and IL will be equals to 25 milliampere e to the power minus t by tau prime. VR1 will be equal to e to the power minus t by tau prime, hence 50 volt e to the power minus t by tau prime. VR2 will be equal to minus R2 by R1 e times e to the power minus t by tau prime, which will be equal to minus 75 volts e to the power minus t by tau prime. The waveform obtained for each of these variables is shown over here. The first graph is for VL, this one is for IL, this is for VR1 and this is for VR2. Thevenin equivalent. For the network shown over here, we have to determine the mathematical expression for the transient behavior of the current IL and the voltage VL after the closing of the switch. The initial current II equals to 0 milliampere. Then we are asked to draw the resultant waveform for each. Now, if you observe over here, there are more than one resistor in this network. Hence, we need to reduce this network into its simpler form. Thus, we will apply Thevenin equivalent to reduce the network. Our Thevenin will be 10 kilo ohm. The calculation used to determine R Thevenin is shown over here. Then, we need to determine E Thevenin. E Thevenin will be equal to 6 volt. Now, the reduced network will look like this. We can easily determine tau, time constant, using the resistance R Thevenin and the value of the inductor L, which is 80 millihenry. Tau, time constant, will be equals to L divided by R Thevenin, which is 8 microsecond. Now, we can determine the maximum current flowing through the circuit when the inductor will reach steady state. In that case, Im, the maximum current, will be equal to E Thevenin by R Thevenin, which is 0.6 milliampere. Substituting these values in the expression of IL, we can determine IL to be equal to 0.6 milliampere 1 minus e to the power minus t by 8 microsecond. And then we can determine VL using the formula VL equals 6 e to the power minus t by 8 microseconds. The waveform for VL and IL will be as shown over here. Inductors in series and parallel. For inductors in series, the total resistance LT is found in the same manner as the total resistance of resistors in series. That is, LT will be equal to L1 plus L2 plus L3 till Ln. For inductors in parallel, the total inductance is found in the same manner as the total resistance of resistors in parallel. That is 1 by LT will be equal to 1 by L1 plus 1 by L2 plus 1 by L3 till 1 by Ln. Example 6. Reduce the network in figure 11.5a to its simplest form. As we can see that inductors L2, L3 and L4 are connected in parallel. Hence, the total inductance of the parallel combination will be LT double prime, which is equals to 0.45 Henry. Now, the parallel combination is in series with L1. Hence, the total inductance for the network LT will be equal to L1 plus LT double prime, which will be equal to 1.01 Henry. And the reduced network will look like this. Energy stored by an inductor. The energy stored by an inductor can be defined by the expression W stored equals half LIm square, where Im is the maximum current flowing through the network. In other words, Im indicates the current through the network when the inductor has reached steady state condition. Example 7. Find the energy stored by the inductor in the circuit in figure 11.66 when the current through it has reached its final value. The current through the circuit will reach its final value when the inductor will reach the steady state condition. That is, the inductor can now be replaced by the short circuit equivalent. Hence, we can determine the maximum current through the network Im using the expression E divided by R1 plus R2, which will be equal to 3 ampere. Then we can determine the energy stored using the following expression half LIm square, which will be equal to 27 millijoule. Steady state conditions. For all practical purposes, an ideal inductor can be replaced by a short circuit equivalent once steady state conditions have been established. Recall that the term steady state implies that the voltage and current levels have reached their final resting value and will no longer change unless a change is made in the applied voltage or circuit configuration. For all practical purposes, our assumption is that steady state conditions have been established after 5 time constants of the storage or release phase have passed. For the circuit in figure A, for example, if we assume that the steady state conditions have been established, then the inductor can be removed and replaced by a short circuit equivalent, as shown in figure B. The short circuit equivalent shorts out the 3 ohm resistor, and the current I1 is determined by the formula I1 equals E by R1 equals 10 by 2, which is equals to 5 ampere. For the circuit in figure 11.61, the steady state equivalent is shown in figure 11.61b. This time the resistor R1 is shorted out and the resistors R2 and R3 now in parallel. So I will be equal to E divided by parallel combination of R2 and R3, which is equals to 10.5 ampere. Applying the current divider rule yields I1 to be 7 ampere. The network used in this example is an RLC network. It has resistor, inductor as well as capacitor. So, if we evaluate this network under steady state condition, then this inductor will be replaced by its short circuit equivalent and the capacitor will be replaced by the open circuit equivalent. As soon as we replace the capacitor with the open circuit equivalent, I will be equal to 0. Then we can determine the load current IL using the formula E divided by R1 plus R2, which is equals to 2 ampere. We can determine the voltage across the capacitor VC using the formula R2 times E divided by R2 plus R1, which will be 6 volt.